Global consumer goods logistics runs at a relentless pace. Thousands of containers shift across the map every hour, maintaining a continuous physical flow of inventory. But behind that physical movement is an equally dense, highly complex flow of financial data. To balance the books, a corporation must reconcile millions of disparate logistical data points every single day. That requires aligning four distinct and often conflicting records: the internal ERP purchase orders, the warehouse receiving logs, the negotiated TMS contract rates, and the unstructured carrier freight invoices. Engineering teams usually default to pushing all this data into a centralized cloud data warehouse. But forcing high-frequency, multi-way joins across these massive tables introduces severe network latency and high compute costs. The engine chokes under the overlapping workloads. Reconciling at the speed of the physical supply chain requires moving the computation out of the central cloud and into a decentralized hybrid pipeline. By structurally decoupling the analytical processing, the transactional state management, and the semantic mapping into specialized engines, an enterprise can drive toward millisecond reconciliation without the infrastructure overhead of a central warehouse. Let's build this architectural blueprint from the edge, starting with the ingestion layer. The initial obstacle is the arrival of a raw, unstructured carrier PDF invoice. Standard relational databases require ordered tables, making them incapable of processing variable document layouts. We resolve this by placing a Vision LLM at the pipeline's front. As the PDF enters, the model extracts the raw text into a strictly formatted JSON payload. This component isolates and extracts the header dates, the bill of lading numbers, and the individual line item charges into standardized, queryable fields. We have converted images into text, but extracting data to JSON is only a structural fix. It fails to solve the problem of contextual meaning, leaving the analytical pipeline vulnerable to the entropy of carrier naming conventions. The accessorial fee problem is a major blind spot in logistics. Carriers use vastly different terminology to describe the exact same charge. One vendor bills an FSC tax, while another bills a peak diesel adge. Standard deterministic matching logic, like regex or Levenstein string distance, breaks down when the naming conventions diverge this drastically. To fix this, we route the text through a vector database, like pgvector. An embedding model translates the ambiguous text string into a mathematical coordinate, plotting it as a vector in three-dimensional space. By executing a proximity search, the database finds the nearest semantic neighbor. It maps the carrier terminology directly to the internal general ledger code for fuel surcharge. Resolving carrier variance at the point of ingestion ensures that the downstream engines receive a consistent set of tokens, significantly reducing the noise that typically plagues automated financial matching. With clean data secured, we reach the analytical core of the blueprint, DuckDB. DuckDB is an in-process columnar database. Running locally in memory, it bypasses cloud network transit times. The engine simultaneously ingests three massive data streams: normalized invoice JSON, ERP purchase orders, and TMS rate cards. The engine immediately hits the Tier 1 logic gate, a three-way quantity match verifying the purchase order against the goods receipt and the invoice.
Next, Tier 2, validating the contractual rate card against the specific shipping lane. Finally, Tier 3, auditing all accessorial fees against pre-approved tolerance thresholds. There is a specific architectural constraint to manage here. Because DuckDB is a single-node engine, unindexed multi-terabyte cross-joins risk memory saturation if they aren't properly bounded. But when optimized, executing these multi-tier rules locally in memory transforms a process that takes legacy warehouses several minutes into a computation measured in milliseconds. Sustaining that speed requires strict workload separation. Analytical reads cannot be slowed down by transactional row updates. Following this principle, the data flow exiting the DuckDB block forks. Cleanly matched invoices process automatically, while discrepancies are flagged and routed downward into an isolated state engine. That engine is PostgreSQL, serving as the dedicated transactional state store for the platform. PostgreSQL specifically manages live workflow statuses, holding invoices in pending, dispute, escalated, or paid states, while operating the queues for human review. The OLAP engine receives state updates asynchronously from this transactional database. Isolating human exception handling and a dedicated transactional layer ensures the analytical core remains frictionless. A single disputed invoice will not lock up the entire enterprise data pipeline. Once the data is processed, we hit the final hurdle: financial compliance. Auditors require the ability to verify why a payment was approved based on historical rate cards that may have since changed. To solve this, the approved and resolved data streams flow into Duck Lake, operating as the storage and auditability layer. Duck Lake combines the cost-effectiveness of columnar Parquet files on object storage with a lightweight relational metadata catalog. The core compliance mechanism is snapshot isolation. Every delta write to the storage layer automatically creates an immutable historical record. Auditors can execute time travel queries, inspecting the exact state of an invoice as of a specific past date, without maintaining bloated, duplicate temporal tables. This approach converts static storage into a high-fidelity record of every decision, providing the forensic evidence needed for rigorous financial reporting and enterprise audit compliance. Local microservices enable execution speed, but enterprise leadership still requires centralized global visibility into logistics spend and carrier SLA compliance. Zooming out to view the entire architecture, we introduce the final component, MotherDuck, operating as the cloud hybrid data product layer. Local DuckDB instances sync with MotherDuck, allowing analysts to execute centralized collaborative queries and share data at cloud scale without heavy infrastructure overhead. The system flow is now complete. Unstructured PDFs are parsed by Vision AI. Semantic chaos is mapped and resolved by vector embeddings. DuckDB executes the multi-way match in memory. Postgres manages the human state workflows, and Duck Lake locks down the audit trail. Every component in this blueprint was selected specifically to address the unique bottlenecks of supply chain data flows. Modern logistics demands an architecture that matches its own physical complexity, a system of specialized engines orchestrated to operate in a high-speed hybrid state.